if two people are of identical geometrical proportions, that is, you have one person proportioned like so, kind of a fat-headed person, and another person of the same proportions but larger, another fat-headed person, and those aren't supposed to be male, female, or anything. It just occurs to me in having drawn this that it might look like a female with a hairdo, but these are just schematic depictions of human beings, so there's no gender implied by any of that shape. But the point is that if this individual is, let's say, twice as tall as this individual, then if they're geometrically proportional, this individual will be twice as wide as this individual and twice as thick as this individual. And the result is that since the person's height, width, and thickness all double, you're going to have 8 times the mass of the person. 2 times 2 times 2. Now the point is that we're not going to go into a lot of detail on that simply because your text doesn't. I usually do, and I would love to. But I'm going to confine myself somewhat unwillingly to just the kind of stuff the text talks about. So here is the rule for weight. Okay, weight is proportional I wrote equal. Let's see if I can rescue that. Weight is proportional and seem to be having a little trouble writing what I think I intend to write. That their weight is proportional to the cube of height. Again, in this case, that's because if the height changes by a certain factor, so does the width and the depth. So all three things change by the same factor. Now, as you've probably read in your text, this means that weight will be of the form kx cubed. And this is a variation. Equation for something that's proportional to the cube of something else. Now, if the weight equals kx cubed, then we know if we substitute a w and an x for one case, that would be, let's say, for the person we know that 75 pounds equals k times 4 feet cubed. This is the information for the 4-foot individual. Now, when we cube 4 feet, we get 64 cubic feet. So if we want to find k, we see that k equals 75 pounds over 64 cubic feet, which is approximately 1.1, let's see, 64, that'd be about 20, it's about 1.16 pounds over cubic feet, or feet cubed. It's not really cubic feet in this case, although it looks like it. So we solve for k in these two steps, and now we write the variation equation with the known value of k, which is w equals 1.16 x cubed. Looks like we're bouncing here a little bit. Then finally, to find the weight of a 12-foot individual, we substitute the known info for the second case. Then we simply cube the 12 and multiply by 1.16. Now you can do that yourself. 12 cubed is 1728. If we multiply that by 1.16, we're going to add almost 300 to that, and that's going to be pretty close to 2,000 pounds. Now I should have written that this was pounds over feet cubed, but I kind of suppressed the units here just to get the arithmetic as clear as possible. So this is the weight of the second case, which is the second individual. Now, 75 pounds for a 4-foot tall human being is reasonable. Turns out so is 2,000 pounds for somebody 12 feet tall. That would correspond to about 250 pounds for a 6-footer. Now, when I say that's reasonable, that's actually kind of heavy for somebody 4 feet tall. It's kind of heavy for somebody 12 feet tall, too. I wouldn't want to have to support that much weight on my leg bones. Even though the leg bones are a little bigger, it turns out that their proportionality isn't as advantageous as the weight proportionality, and we might look at that a little bit later. But this is the basic procedure for variation. We write down the variation equation. We substitute the known values for one case. We solve for the proportionality constant. That's what we call K, the proportionality constant. We rewrite the variation equation for that proportionality constant, and then we substitute the known information for our other case to get the unknown information for that case.